This grid locates algorithm 23, Apriori, inside the association rules category. We are moving from clustering abstract data points to extracting definitive rules about how different physical items interact with each other. Every day, retail checkouts process thousands of independent purchases. Within those scanned receipts are invisible connections, groups of items that customers consistently buy together. Traditional analytics struggle to detect these specific pairings when they are buried in a mountain of unrelated noise. In 1992, researchers at NCR and Teradata took on a massive analytics project for the Osco drug chain. They wrote SQL scripts to mine roughly 1.2 million physical market baskets across 25 different stores. Among the 20 or so unexpected product pairings they found, one stood out. They noticed that between 5 and 7 p.m., customers buying diapers were often buying beer at the exact same time. The working theory was that young fathers picking up baby supplies after work were grabbing a six-pack for the evening. That specific correlation circulated through the tech industry and became famous data mining lore. But Osco Drug never actually moved the beer next to the diapers. Finding a pattern is only half the battle. You still need a secondary step to mathematically judge whether that correlation is a trivial coincidence or a highly actionable rule. Extracting these patterns from a database presents an immediate mathematical trap. If you try to find associations by brute force, checking every possible combination of items against every historical receipt, you trigger an exponential explosion of possibilities. This chart shows the severity of that candidate explosion. Because the complexity scales at O of 2 to the power of n, a store with just 30 unique items generates over 1 billion possible combinations. A standard generation and test approach forces the system to complete a full database scan to verify every single level of those combinations. This creates a massive I/O bottleneck that will quickly crash standard hardware. In 1994, IBM researchers published a solution specifically designed to navigate around this computational wall. They called it the Apriori algorithm, named for its defining technique of using prior knowledge to aggressively prune the dataset. Instead of relying on raw processing power to grind through billions of item sets, Apriori treats the search like a logic puzzle. It uses the mathematical properties of subsets to identify impossible combinations and skip calculating them entirely. The engine driving this algorithm is a concept called the a priori property, which data scientists refer to as downward closure. The positive rule of downward closure is straightforward. If a large group of items frequently appears together in customer baskets, then every smaller subset of those items must also appear frequently. This diagram outlines the inverse rule, where the algorithm gets its power. If a single item or pair is infrequent, mathematically, every larger set containing it is guaranteed to be rare. The algorithm builds candidate item sets level by level. It isolates frequent single items in L1, joins them to test pairs in L2, and combines surviving pairs into triples in L3. If a specific pair fails the minimum frequency threshold in L2, the algorithm stops testing it. Any future combination relying on that failed pair is instantly killed, completely bypassing the database scan for those larger sets. This flowchart tracks the complete logic loop. The system generates a K item set, scans the database to verify them, prunes the failures, and cycles back to generate the next level up, repeating the process until no new frequent item sets remain. By refusing to count supersets of rare items, Apriori prevents the candidate explosion, successfully mining vast, complex databases in a fraction of the expected time. Once the algorithm isolates the frequent patterns, the focus shifts. The system must score these surviving item sets to construct valid business rules. This layout breaks down the three metrics used to judge a rule. First is support, measuring raw frequency, the percentage of all transactions containing a specific pattern. Second is confidence, tracking conditional probability, the likelihood that buying item X actually leads to buying item Y. This Venn diagram maps out how confidence isolates those probabilities. The algorithm calculates the ratio by comparing the total transactions containing item X to the specific overlap in the middle where customers bought both items together. Returning to our scoring panel, we see the final arbiter, lift. This metric calculates the ratio of confidence to expected chance. A lift greater than 1 proves the items positively attract each other, rather than just appearing together randomly. A rule might have high confidence simply because one of the items is incredibly popular. Lift filters out that baseline popularity, separating actionable business intelligence from inexplicable noise. Applying these precise metrics allows retailers and digital platforms to automate their recommendation engines and optimize store layouts based on verifiable data. Cascading streams of chaotic transaction data are systematically filtered, snapping into isolated pairs that represent highly valuable commercial insights. Apriori isn't flawless. Because it still requires a full database scan at each iterative level, it slows down significantly when processing extremely dense modern datasets, a limitation that newer methods like FP growth were built to solve. To prevent the system from returning thousands of useless correlations, human engineers must carefully define the minimum support and confidence thresholds before execution, manually tuning the algorithm to find the exact scale of patterns they need. First, grow the item sets, prune the rare ones to find a pattern, and score with lift to judge the reality. Open up the provided Python notebook, input your thresholds, and watch these association rules fall out of your own data.
The opening steps to mine association rules are entirely administrative. We import pandas for data manipulation and pull in the PyFP growth library to serve as our pattern finding engine. Then we feed the engine its raw material. Here, the dataset is a simple dictionary representing 4 specific shopping baskets filled with cricket peer. But look closely at the third basket. Someone entered pad, singular, while the previous basket lists pads, plural. Algorithms process exact tokens. To this logic engine, pad without an S is an entirely separate, unrelated object. It does not recognize them as variations of the same product. Before a single mathematical operation runs, the pipeline's output is already constrained by the messy, inconsistent reality of human data entry. Moving down the pipeline, we hit the first operational function, find frequent patterns. The second argument in that function, the integer 1, is the support dial. It dictates exactly how restrictive the algorithm will be. This diagram shows the counting mechanism. The algorithm scans level by level, tallying items in pairs and triplets. Setting our support dial to 1 forces the algorithm to keep any combination appearing in at least one basket. Anything below that threshold is pruned. Turning that dial up requires an item bundle to appear frequently to survive, isolating only the most common pairings. Turning it down rescues rare, niche combinations, but forces the computer to process an exponentially larger list of candidates. The support function acts as a brutal gatekeeper. It strips away the mathematical clutter to leave a concentrated pool of actual, recurring bundles. Next, we pass those surviving patterns into the generate association rules function. Here, we encounter a new parameter set to 0.3. This is the confidence dial. This breakdown transforms bundles into directional rules. Confidence measures conditional probability. If out of 4 diaper baskets, 3 contain beer, confidence is 75%. Setting our dial to 0.3 discards any rule correct less than 30% of the time. While the support dial gathered the raw materials, the confidence dial filters for probability. It shifts the focus from how common a bundle is to the likelihood that one item actually follows another. That is the complete execution pipeline. We import the data, the computer follows these instructions literally. It applies the same mathematical filters and yields the same set of rules every time the code is run. But the code has no context for the real world. It doesn't know what a cricket bat is. It cannot distinguish between a groundbreaking consumer insight and a random statistical coincidence. The math will happily output a rule stating that people who wear red shirts score higher on exams. Sorting that output into trivial facts, inexplicable flukes, or actionable business strategies requires actual domain knowledge. Mining a massive database for association rules requires only a few fast lines of code. Extracting actual value from those rules remains an exclusive. How do we actually sift through that endless digital warehouse to find the specific patterns that drive revenue? This diagram illustrates a simple mathematical concept.
Look at the pink zone in the center. That intersecting logic drives the frequently bought together recommendations you encounter online, and its utility goes far beyond retail. This exact logic is deployed to mine web clickstreams, group complex medical symptoms, and scan for network intrusion signatures in cybersecurity command centers. Finding these hidden correlations turns a chaotic pile of logs into actual predictive power. So, in an era dominated by advanced deep learning, why do data engineers still actively choose to deploy a classic tool like the a priori algorithm? The answer comes down to absolute interpretability. Neural networks operate as opaque black boxes, but a priori produces simple, human-readable if-then statements. It is also completely unsupervised. You can feed it raw, unlabeled transactional logs, and it will digest and organize them without needing human categorization first. Look at the flowchart here. By adjusting the threshold at the prune step, engineers cut out irrelevant data. Because of this iterative loop down to the final decision gate, the process is deterministic, highly auditable, and easily explained to non-technical stakeholders. When you absolutely must be able to prove how your system reached its results, a priori is the transparent workhorse engineers trust. However, that elegant transparency exacts a heavy toll on large datasets. The algorithm suffers from a mathematical flaw known as candidate explosion. As the bottom box outlines, the required solution for scale is FP growth. This newer algorithm solves the bottleneck by compressing the database into a tree structure, entirely eliminating candidate generation. A priori handles smaller, sparse baskets beautifully, but when scale overtakes the need for step-by-step interpretability, graduating to FP growth is mandatory. Despite the mathematical rigor required to extract these rules, the algorithm possesses zero real-world context. The logic mapping these engineering decisions is drawn directly from 50 algorithms every programmer should know. A priori remains the plain-spoken engine of discovery. It is easy to read, easy to trust, and operating quietly behind almost every recommendation you encounter.